Hi everyone, my name is Murtaza Dalal. I'm a PhD student at Carnegie Mellon, and I'm very excited to talk to you about our work on building generalist agents for robotic manipulation. This was work done with my co-lead, Min Liu, collaborators at Apple, and of course, my advisors at CMU. As a teaser, I want to show you our final result, ManipGen, a single generalist agent across manipulation tasks. This is a text-conditioned agent that performs zero-shot, long-horizon manipulation. We deployed on 5 different tasks with a variety of different setups, which I show here. I really want to emphasize these tasks are quite difficult, much harder than what you would see normally, because these scenes are extremely complex, with many obstacles, objects, and receptacles. This single agent has to perform collision avoidance, generalize to arbitrary objects, and perform constrained manipulation. All of this completely zero-shot, just from text input. So you might be wondering, how did we get here? Well, that is going to be the focus of today's talk. So let's start off with some motivation. Let's watch this video of a person opening a door, and you'll see that there's clearly 2 stages. One in which we reach a pre-contact pose, in this case the door handle, and then there's contact-rich interaction, actually turning the handle and pulling open the door. Maybe we can use this idea to decompose manipulation tasks? Let's instantiate this by defining a new policy class, local policies, as policies that are initialized close to the object of interest, or interaction point. This is the initial state distribution. They take in local observations, just in the vicinity of the object or interaction point, and take local actions in that region, aka relative actions. They look something like this. These local policies have some great properties. They're invariant to absolute pose because they only care about the relative positioning of the hand and the object. They're invariant to skill ordering since we can use motion planning to take care of the chaining problem. I'll talk about this in more detail later. And finally, and most importantly, they're invariant to the global scene configuration because they only care about the local region around the object, which means it's much simpler to generate data for them at scale. The core idea of ManipGen is that these local policies enable us to scale learning for manipulation in simulation and transfer it to the real world in a modular structure to solve a wide variety of different tasks. As an overview of this work, ManipGen first uses RL to acquire local behaviors at scale. Then we distill these thousands of experts into a single visual motor policy per skill. And then finally, we deploy these policies zero-shot in challenging environments by using a VLM to plan, a motion planner to reach poses near objects, and local policies to perform manipulation. So how do we actually acquire local behaviors using RL? Well, for the observations, we found it important to include a significant amount of privileged information in this phase, which we do so by incorporating shape information and components of the reward. For the reward itself, we have a general formulation that looks something like this. Here, REE, RObj, and RSuccess specify the behavior of the skill, while the other 2 rewards constrain the motion of the policy, making it easier to transfer sim to real. Now, putting everything together, we pass the privileged and proprioceptive state information into the policy, and we train these policies using PPO at scale. To see our local policies in action, check out these videos of the pick, place, grasp handle, articulated object opening, and closing skills. For pick and place, we sample random clutter and distractor objects and encourage the agent to only interact with the target object, here shown in red. One thing to really emphasize here is that due to locality, we can make the simulation environments dead simple, but we can still generalize to complex, real-world scenarios. The reason this is possible is that we are invariant to global scene configurations, since we only observe things locally. Now that we've acquired behavior, we need to distill all of these single task experts into a single generalist policy per skill. The key to doing this is using online imitation learning. Since RL policies can give us dense feedback at any state, they're queryable experts, so we can just do multitask dagger. Now, for the observations, We opt to use wrist camera observations, which are of course local. Once the policy gets super close to the object, it might have some difficulty in telling what's going on, so we also incorporate the first frame, which generally has a clear view of the object. We also need to communicate which object to interact with, so we pass in a segmentation mask of the target object, which we can easily get in the real world using grounded SAM. Now, for local policies, we found that you actually don't need an enormous sequence model to fit the data really well. So here we opt for a ResNet 18-based architecture with a spatial softmax at the end, and then we use an MLP decoder to predict delta and effector control actions, and just train with MSE loss using multitask dagger. So now the question becomes, how do we actually deploy these visual motor local policies in the real world? For that, we build on prior work on planned sequence learn, which used a hierarchical decomposition to efficiently train specialist policies for challenging manipulation tasks. A quick sidebar. PSL uses an LLM to decompose the task specified via natural language into a coarse high-level plan. It then uses vision and motion planning to actually step through the plan, which is done by estimating the pose of the target object and then motion planning to it. Finally, it uses RL policies to efficiently learn local environment interaction. However, this is all done in the loop to learn a specific task. The core challenge now is moving from this specialist approach to a generalist approach for manipulation. For each step, we will use learning at scale to build generalists with specialized capabilities and then combine them to massively amplify their generalization. First, to perform real-world task planning, we need the agent to perceive the environment, which requires the use of some sort of a VLM instead of an LLM. Here we use GPT-4o, as we found that VLMs trained on internet-scale data perform quite well. Next, for fast, reactive, real-world motion planning, we want to use a motion planner that can operate on noisy point cloud input. Here we use Neural Motion Planner, an end-to-end policy for performing fast motion planning in the real world. Finally, we come to the core new piece of ManipGen, which I just described. To train generalists that can solve new tasks in a zero-shot manner, we need pre-trained skills, which we obtain by scaling up learning in simulation and transferring sim to real. Having defined all of these components, let's quickly walk through an example deployment. Here we use the VLM to come up with a plan for the scene given views of the scene and text prompt. It comes up with a plan in terms of the skill library using the formatting I show here. We then deploy this plan open loop, estimating where to go using grounded SAM to segment the target object point cloud, averaging it to get a position, and sampling collision-free poses that point at the object. We alternate between pose estimation, neural MP, and running the right local policy until the task is solved. Okay, let's quickly look at some results. We evaluate ManipGen on 5 different diverse tasks, achieving high success rates across each task, at least 60% on the hardest, long horizon tasks, with up to 90% on some challenging multi-stage manipulation tasks like storing items in the cabinet. Our tasks are extremely challenging, requiring the agent to perform pick and place, articulated object manipulation, constrained tight space manipulation, all of this entirely zero-shot from text prompts. We evaluate using a diverse object set, varying the objects to manipulate and the receptacles for every task, with strong pose randomization to ensure that we're really stress testing ManipGen's generalization capabilities. Note, we did not directly train on any of the objects we evaluate on. Instead, by training local manipulation at scale, ManipGen is able to generalize broadly. In terms of numerical results, we showed that our method beats out some very relevant baselines in terms of text condition manipulation. We include the success rate per task as well as the average number of stages completed, essentially logging the average progress along the task. We also have more results in the paper with comparisons in simulation, as well as more real-world tasks, comparing against end-to-end RL, BC, task and motion planning, and more LLM-based planning methods. And with that, I thank you for listening, and for additional details, including videos, experimental setups, and implementation details, please check out our website linked on the left and read our Twitter summary on the right.